This is lesson 7.5. We're just going to be talking about the special distributions. All right, the first one we're going to talk about today is called a binomial distribution. And the second one we're going to talk about is the geometric distribution. So today is binomial, tomorrow is geometric. All right, so these are very special distributions. And after that, we're going to talk about a continuous one called a normal distribution, which we actually mentioned already in a previous chapter. But binomial and geometric, these are for discrete numerical variables. All right, discrete numerical variables. So let's focus on the binomial today. All right, now, guys, the binomial experiment or binomial situation is a very, very specific situation. Like you can only use the stuff that we're going to learn today in a very specific situation. And there's 4 criterias, okay? So you know you're in a binomial experiment if, number 1, there's a fixed number of trials. There's a fixed number of trials. So for example, let's say a trial is like rolling a die. All right, so rolling a die, and let's say specifically you're going to roll the die 5 times. All right, you're going to roll the die 5 times. That's a fixed number of trials because the fixed number is 5. All right, you're rolling the die 5 times. All right, so n is to denote the fixed number of trials. So in this case, my example, n would be 5. All right, n would be 5. All right, so that's number 1, criteria number 1, you have a fixed number of trials. Criteria number 2 is each trial results in one of 2 mutually exclusive outcomes. One will be labeled success, one will be labeled fail. So there's only 2 outcomes. All right, there's only 2 outcomes. So for example, rolling a die, there's actually 6 outcomes, right? 1, 2, 3, 4, 5, 6. So that would not be considered, satisfying this criteria. But we can make it satisfy it by saying like, we're only going to be looking at if the number is even or odd, right? Even or odd. Now you only have 2 outcomes, even or odd. So that's okay. Or you can think, I want to roll a 6. So I'm going to label rolling a 6 a success, and then a failure would be anything not a 6. Then those would be considered 2 outcomes, and it will satisfy this. Okay? So that's criteria number 2. All right, 2 outcomes. 2 outcomes. All right, number 3, the outcomes of the trials are independent. All right, so independent, just like we talked about in previous chapters, independent means one trial doesn't influence the other trial. So when I roll a die, whatever I get on my first roll will not impact what I get on my second roll. So those are considered independent trials. All right, and the last criteria for it to be in a binomial situation is that the probability of success needs to be the same every single trial. All right, it's the same constant. All right, so let's say, I'm rolling the die and I'm saying rolling a 6 is a success and not rolling a 6 is not a success. All right, it's a fail. This would satisfy because the probability of me rolling a 6, a success, is 1 out of 6 every single trial, right? It stays constant every single trial. Okay, so if these 4 criteria are met, then we have a binomial experiment. And if we have a binomial experiment, our variable, all right, x, we're going to label x. What we're always looking for is how many successes are there in those fixed number of trials. So if I roll a die 5 times, and I'm saying rolling a 6 is a success, how many 6s did I roll? That would be considered my random variable, x, the number of successes. All right, so this is how we know we are in a binomial situation. Let me take a pause and see if there's any questions on these 4 criterias to being in a binomial experiment. You can put it in the chat or you can unmute yourself. Let me actually give you guys an acronym that will help you remember this. All right, in true Mrs. L form, I have an acronym for you. All right, so hopefully this helps you guys remember these. So your acronym is bins. All right, bins, like a box. So bins stands for binary outcomes. All right, so this is the success or fail. I'll just do SF. All right, so you have binary outcomes. You have independent trials. N is the number of trials is fixed. All right, so that's your N variable. Oops, sorry. And then your S is that the success probability is constant. All right, so bins. And then just so you guys know, the variable we're going to use for that success probability is P. All right. So that is your acronym. All right, let me give you guys a moment to copy that down. Okay, if you guys need that again, let me know and I can go back to this later. Okay, so let's go ahead and practice this and see how to tell when a situation is a binomial situation. All right, so I'm going to give you guys some scenarios and I want you to walk through bins and see, does it satisfy those 4 criterias or does it not? All right, so number 1, toss a coin 10 times, count the number of heads. Okay, toss a coin 10 times, count the number of heads. All right, so I'll show you how to do it on this one first. So starting with bins, binary outcomes, B. Do I have 2 outcomes? Heads, not heads. Yes, heads or tails, right? Binary outcomes, so B satisfies. I, independent trials. Every time I flip the coin, it doesn't affect the next flip. So yes, I have independent trials. N, number of trials is fixed. Yep, I'm tossing the coin 10 times. Exactly. So that number is fixed. I have fixed number of trials. And then S, success probability is constant. Yes, the probability of getting heads every single time is 50% every single time. So this is considered a binomial distribution. So this meets the criterias. Okay, so let's have you guys try the next 2. Okay, so number 2, deal 10 cards from a shuffled deck, all right, and count the number of red cards. So deal out 10 cards from a shuffled deck and count the number of red cards. So everybody in the chat box, go ahead and write yes or no. All right, so go through bins, 4 criterias, yes or no. Is this a binomial distribution? Okay, good, good. Good, 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 good. Good, good. Nice, perfect. Everybody got the right answer so far. So, Scott, let me ask you, why did you say no? Why is this not considered a binomial distribution?
I'll be honest, I kind of just guessed this one.
Okay, that's all right. Let's walk through bins. Well, you guessed it right, so good job. All right, so let's go through bins. B, do we have binary outcomes?
No.
So binary just means like 2. Are there just 2 possible outcomes every time you flip a card over?
Yeah.
Right, because what are the 2 outcomes?
It's the 2 sides.
Oh, well, looking at this, we're looking at the color of the card. So every card is either what?
The red side or the other side. Or is it red on both sides?
So it's not front or back of the card, it's actually the color of the card. So when you look at the color of the card, it's either red or black. Did you know that?
Right.
Okay. So that's what I mean by binary outcomes. When you're looking at the color of the card, it's either red or black. There's
Hmm.
there's no blue, there's
So
no
that's the binary part.
that's the binary part. Yes. So looking at the card, it's either red or black. Just like when you flip a coin, it's either heads or tails, right? So there's
Hmm.
two outcomes. Okay. Let's go I. I is independent trials. Does this satisfy independent trials?
Um, I think
Okay, so the question you want to ask is every time I flip a card out, does one card's, I guess, what comes out after one card, does it affect what's coming out for the next card?
no,
Not really, but maybe kind of, depending if you replace the card or not. So if we don't replace the card, then are the flips independent? Like if I flip a red card, flip a red card, flip a red card, flip a red card, is that going to affect what I get next?
not really. I mean, the less red cards, the more chance you have to get a black one, right?
Exactly. Yeah. So it does affect it, right?
Mm-hmm.
Because as I'm flipping these red cards, it affects the chances of my next card being black or red. Because now I have less red cards, I have more black cards. The chances of me getting a black card next is getting higher if I keep flipping red cards. So I would say that it's not going to satisfy because number one, the trials are independent. And then two, the success probability also isn't staying the same. Because instead of out of 52 cards, my next draw is out of 51 cards, then out of 50 cards, out of, you know what I mean? Like the
Yeah,
probability changes. So I would say no, because that probability doesn't stay the same and the trials are not independent. Does that make sense?
yeah.
Yeah? All right. Good job, Scott. Nice. Okay, let's try another one. So this one, same thing in the chat. Say yes or no if you think it is a binomial distribution or not. Okay, so number three, the number of tickets sold to children under 12 at a movie theater in a 1 hour period. Try this one. Yes or no in the chat. Good. Mm-hmm. Good, good, good. All right, good job. Okay, so let me go ahead and ask Megan G. Why no? You got it right, but
Yeah.
why not?
Isn't it because there's no like binary outcomes?
Okay, so what are the possible outcomes then?
Like they'd be under 12 or they'd be over 12. Is that it?
That actually is, yeah. So then
Okay,
that,
I didn't think it was.
yeah,
So
no, you're
maybe
right.
yeah.
So binary outcomes, that actually is yes. Like there is binary outcomes. It's either under 12 or not under 12. So that actually satisfies. There's something else that it isn't is why it's not a binomial distribution.
Um, is it the number of trials?
Uh-huh. Because
Okay.
it's not what?
Um, I don't know.
Like we need the number of trials to be what for it to be a binomial distribution?
Oh, it needs to be fixed.
Yeah, you need like a set number. Like we're gonna look at the next, 25 tickets. That would make it okay. But in this case, it's just a set number of time, not a set number of tickets. So great job, Megan. Nice. So no fixed number of trials. So this would be no. All right, good job, guys. In the chat box, if you guys can just let me know if you feel like you understand, how to tell if it's a binomial distribution, put yes. If you're still like, no, not really, put a no. Or if you're like, kinda, go ahead and put kinda. So, do you understand how to tell if something is a binomial distribution? Yes, no, kind of. Go ahead and put that in the chat. All right, so now that we know how to tell it's a binomial distribution, let's use our calculators and we're going to answer some probability problems based off of the situation. So our example is, let's record the gender of the next 5 newborns, babies, at Huntington Memorial Hospital and see how many girls we get. So this is a binomial experiment. All right, we're assuming, each trial is 1 baby, okay? And we want to, see if it's boy or girl. So binary outcomes, independent trials, right? 1 baby's gender doesn't affect the next baby's. Number of number of trials is fixed at 5. And the probability of success is 50% chance of a girl, all right? 50% chance of a girl. So since we're seeing how many girls we get, we're gonna set X, our random variable of interest, to be X, the number of females born out of the next 5 births, right? So X is the number of girls born out of the next 5 births. And if that is our X, the possible values are, well, we can have 0 girls out of the next 5 babies. We can have 1 or 2 or 3, 4, or maybe all 5. All right. So these are the possible values that X can be. So this is a discrete variable, right? This is discrete. Okay, so let's get into some probability. So the probability of success in this case we said was 50%, right? 50% chance of a girl. But we want to know, what is the probability that exactly 2 girls will be born out of the next 5 babies? All right, so at Huntington, if we look at 5 babies, what's the probability that exactly 2 of them will be girls? Okay, so here is where you need to take out your calculator. All right, so on your calculator, where you guys are gonna go is you're gonna go second, so the blue button, and then vars. Above it, you see distribution. You're gonna click that, and you should see this screen. All right. So on this menu, go ahead and scroll up to get to the bottom of it, and then you see right here, A and B, we have binom PDF and binom CDF. All right, so I'm going to teach you guys how to do binom PDF and CDF today. So binom PDF, if you click enter, it asks you how many trials. All right, so in this case, we have 5, right? We're looking at 5 babies. P stands for the probability of success, so that's 0.5. And then X, we're looking for what's the probability of getting exactly 2 girls, right? 2 successes. And then you click paste and then press enter. And that is your answer, all right? 0.3125. Now, on your notes, do not just write the number here. Write down this whole thing. Binom PDF parentheses 5, 0.5, 2. This is the work that you have to show if you want any credit on that quiz. All right, so make sure you show this setup. Okay, so write that down plus your answer of 0.3125. All right, questions on that?
Where did you get the 0.5?
That's the probability of success. So the probability of getting a girl on each trial, there's a 50% chance that 1 baby turns out to be a girl. All right, so yeah, so that 0.5 is the probability of success for each trial, for 1 trial. Okay, go for it, Maddie.
I'm kind of confused because I went to the second bars and I went to the binom PDF.
Uh-huh.
But where do you enter it? Because I have all of the values in now, but it just says paste. I don't know what to do after that.
Oh, yeah, press enter on the paste.
Oh, okay.
Yeah.
It just goes to sorry. It just goes to the Y values, the plots. It doesn't show, it doesn't enter.
Okay, so you do see the menu that pops up, right? Like,
Uh,
are you seeing when you do Binom PDF, you
this.
see this?
It goes to that.
Hold on. Okay, all right. So let's go ahead to our next question on here. It says, what is the probability that less than 2 girls will be born out of the next 5 births? Less than 2 girls. Okay. So if you think about, well, less than 2 girls, well, that means either 1 out of the 5 are girls or 0 out of the 5 are girls. So you could actually go second distribution and do binom PDF. Still 5 babies you're looking at. Probability that a baby is a girl is 0.5. And the probability of getting 1 or, so plus 0, you can set up like so. All right, so you can just add those up and find the probability of getting exactly 1 or exactly 0 girls, and you get 0.1875. Now, there is a shortcut to that, which is binom CDF. So if you were to do the same thing with binom CDF, 5 trials, probability of success is 0.5, and plug in 1 for X. Notice we get the exact same answer. Now, the reason behind that is C stands for cumulative. Cumulative. So what your calculator automatically does is it finds binom PDF of 1 and adds that to the binom PDF of 0. Okay. If we change this binom CDF to, let's say, 2 as the last number, then it would do PDF of 2, 1, 0 and add those up. If it did binom CDF all the way up to 4, let's say the last number is 4, then we would do the PDF of 4, 3, 2, 1, 0. So it accumulates it all up until whatever number of successes you want. All right, so this is a nice shortcut to use CDF. All right, so that's how you do that. Okay, any questions on that? PDF or using CDF? Okay, well, here's the work so you guys can see. All right, and this is the work I do want you guys to show me. You don't have to do the P parentheses part, but show me the binom PDF or binom CDF, so that way I know, what you guys are plugging into your calculator. And that way I can also give you partial credit if you're just missing like a little part. Okay, so let's finish this off then with our last set of formulas, which is to find the mean and standard deviation of a binomial distribution. So here are your formulas. Mean is just n times p, and standard deviation is the square root of n times p times 1 minus p. 1 minus p, by the way, sometimes we label that as just q. So if you see q, q is just 1 minus p. All right, so for example, all right, same example. How many girls would you expect in the next 5 births? So when I see expect, I think average. All right, average. So to find the average, I do n times p. N is the number of trials, so that's 5. P is the probability of success, 0.5. So I get 2.5. All right, so on average, you would expect about 2.5 girls. Standard deviation, you would just use square root of np times 1 minus p. So square root of 5 times 0.5 times 1 minus p, which is also 0.5, giving me 1.118. All right, so that is how you find the mean and standard deviation of the entire distribution of the situation. Okay, so in summary, if you guys want to screenshot this is a good kind of summary of everything. All right, you have all our variables defined. N, number of trials. P, probability of success. Q, which you'll sometimes see, is just 1 minus P, which is probability of fail. And X is the number of successes in the fixed number of trials. Okay. Binomial PDF, when you're looking for exactly X number of successes. You can use CDF if you want less than or equal to this many successes. And then these are your formulas for the mean and standard deviation. All right, and that is it for our first lesson.